Okay, Chapter 5, Chemical Reactions. We're starting to put it together. 5.1 we'll talk about chemical equations, and 5.2 types of reactions. Okay, on the very front slide I had a chemical equation that was hydrogen plus oxygen equals water. But I didn't write it like this. I wrote it like this. I used symbols. Now you'll notice I use some symbols that are subscripted, and I use some symbols that are bigger. These are known as coefficients, and of course these others right here are known as subscripts in the red. I'm pointing with the red. The symbols are the letters that we use, and every capital letter, remember, starts a new element. So water is H2O. Now, if you look at this on this side of the equation, and I like to balance it, well, let's talk about balancing here in just a sec. As we write a chemical equation, like we have here, we need to do a few things. We need to check and make sure that we deal with what's called the law of conservation. That means I can't have something appear that wasn't in the left side on the right side. I can't have something disappear on the right side or the left side. So conservation of matter is just that. I'm conserving matter. So for instance, let's take a new equation here. Let's take nitrogen, and nitrogen is one of our Braunhilfe or our diatomics, so that runs around in pairs as an element, so N2 plus hydrogen, and hydrogen is H2, and it's also one of our Braunhilfe. And from that I'm going to make ammonia, and ammonia is NH3. Now, what I like to do is I like to take a scratch piece of paper and I like to butt it up about right here. So this is my scratch piece of paper. And what I do is underneath the arrow, I write all the symbols that are on either side. And I do that leaving H and O to very last. So on this one, since there's only nitrogen and hydrogen, I'm going to go nitrogen and hydrogen. Then I count how many are on the left, and I have 2. And how many are on the right, and I have 1. They're not the same, and so I have to make them the same, and I have to use coefficients to do that. So I put a 2 right here. Now I have 2 nitrogens on both sides. Now I go back to my hydrogen. On the left I have 2 hydrogens, and on the right I have 2 times 3, which is 6 hydrogens. Well, I need to go back to the left and figure out how I can make 6 hydrogens. I can do that by putting a 3 in front of that H2, and that makes 6 hydrogens. I'm now balanced and I've conserved matter. So I've balanced the equation, written the equation, and we're good. Okay, so say I had nitrogen monoxide gas and oxygen gas yielding nitrogen dioxide. Well, writing the formula, nitrogen monoxide, I have nitrogen with 1 oxygen, and is a plus sign. Oxygen gas, oxygen is another one of our Braunhilfe or our diatomics, so we're going to write O2, subscript 2. Yield is my arrow, or produce if they say produce. Nitrogen dioxide, so this time I'm going to go nitrogen with 2 oxygens. Okay, I'm going to take that piece of paper and slide it up right here so I can balance, and underneath the arrow again I'm going to write nitrogen, and then oxygen on this one's going to be last. Remember, hydrogen and oxygen always leave last, like ho ho ho. That's the last thing Santa says, is ho ho ho. So just remember that goes last. Okay, so on this one we have 1 nitrogen on the left and 1 nitrogen on the right. On the left now we have 1 plus 2 oxygens, giving me 3 oxygens, and we have 2 oxygens on the right. Now this one's a little tricky because I only get even numbers on the right. So I need to get the left into an even number. And the only way to get the left into an even number is to take and times this one right here by 2. So let's do that. If I times that one by 2, then I now have 4. Let's see if that helped us on the other side. Well, I now also have 2 nitrogens, right? So now I've got to come back here and times the nitrogen by 2, And by doing that, that affects my oxygen, and I also now have 4. So everything balances out that way. I now have balanced the equation for this one. When we balance an equation, we want to have it in the lowest whole number ratio. So if I looked at this equation, I could have also said it's balanced when I have 4NO plus 2O2 yields 4NO, but that's not in the long mixed common ratio. You can see that I can take that whole thing and divide out a 2. And it, in the same thing, or same line of thought, I couldn't take and say NO plus 1/2 oxygen yields NO2. There are some cases that you use that later, but we are going to only balance with whole number ratios. So these right here, we don't want to do. We do want to end up with a whole number ratio, okay? Okay, so we're going to start another one here where we have iron, and iron, remember, is Fe, and it has a +3 charge because of the Roman numeral 3, and oxygen, which has a -2, and these have to add to equal 0. Well, remember, the common factor between 3 and 2 is 6, so to get this one to 6, I'm going to times it by 2. To get this one to 6, I'm going to times it by 3. And those become the subscripts, so I need 2 irons to go with 3 oxygens. I'm going to take and erase on our mess up here that we did to figure that out. Then we go on to the next thing, and plus coke, which is carbon, just plain C, are heated to produce, so we got an arrow, iron metal, Fe, and carbon dioxide gas, and we know carbon dioxide gas is CO2. Now I can add the gas and the solid at a later time. I'm going to have and balance this by putting my paper up right here. A scratch piece of paper, and there's a whole bunch at the back of the room. You're welcome to use that. It's usually behind your crate. Again, put in order underneath the arrow what ones you have. Now for easy ones you won't need to do this, but when they get a little complicated like this, you will want to do this. Fe, C, and remember leaving ho to last, so oxygen last. Now we're going to balance side to side. So Fe on the left I have 2, Fe on the right I have 1. So I'm going to put a 2 in front of the Fe, and I've got it. On the left I've got 1 carbon, on the right I've got 1 carbon. On the left I have 3 oxygens, and on the right I have 2 oxygens. So we got a little bit of an issue here. So the first thing I want to do is look and say, okay, what's the common factor between 2 and 3? And we know this already, it's 6. So I'm going to go back over here and I'm going to make 6 oxygens on the left by timesing that one by 2. So I can get 6. So I'm going to put 2 up here. But when I do that, that changes my iron. So I'm going to put a 4 here. Now I'm not going to do anything with the iron until I fix the oxygen on the other side. So over here we've got 2 oxygens, which is 3 times we need to get to 6. So I'm going to times it by 3. And I'm going to put a 3 in front of the carbon. Now my carbon and my iron are back off. So going back up to the top to my iron, I've got 4 on the left, I only have 2 on the right, so I need to erase this 2, and this is why it's always a good idea to write it with pencil when you're balancing equations. And I now need 4 over here, so I'm going to put 4. Same thing with the carbon. Now on the carbon I have 3 on the right, and I only have 1 on the left, so I'm going to times that one by 3, and we've got the numbers that we need, and everything is balanced. Okay? Okay, so now we're going to talk about types of chemical reactions. When we talk about types of chemical reactions, this will actually break down into 2 different branches here. The one is non-redox, and the other side is redox. Okay, so let's take the non-redox side and see what happens to it. Non-redox will break down into combustion, double displacement, and decomposition. On the other side, we've got redox, which includes combination, or what I called earlier synthesis, meaning putting together, synthesize. Combination is the same thing. Single replacement, which is a substitution, And decompositions can also be redox. So you got to be careful with decomposition because can be either a redox or a non-redox. So be careful with that one. I forgot to tell you the other name for double displacement is metathesis, and double displacement can also be known as replacement. So a lot of times instead of dis, they'll put re. Okay, so know that it's replaceable. Okay, so what, right? Let's look at each one of these a little bit differently. I like to look at them and give you sort of a description of what each one is. So let's do that in the next slide. Okay, so redox, we have several, and I like to relate it to the dating game thing. So in a combination or synthesis, we have boy meets girl, and they become a couple. In chemical lingo, we would say A compound plus B compound yields AB. Well, in decomposition, it's just the opposite. We have boy and girl as a couple, and what happens? They get in a fight and are no longer a couple. So boy is by himself and girl is by herself. Again, chemical wise, what do we get? We get AB goes to A plus B. Now in single replacement or substitution, we can have a couple, and I know you love my stick figures here, and I'm trying my best to draw stick figures with this iPad thing, but it's not real great. And what happens on this is we have another player. Say that we have another girl that comes along, and maybe she has blonde hair instead, and kicks out the one girl. So we have our boy that is now with the blonde, and the dark-haired girl got kicked out. Now I don't necessarily hold to that, but I'm just letting you see. So that would be like saying A and B plus a D would give A, D plus B gets kicked out. Okay, it also can happen the other way where we have a boy and a girl, but this time we have another boy that comes into play, and we'll make him have spiky yellow hair. And the boy gets kicked out. So now we have the boy with the spiky yellow hair with the girl with dark hair. And the boy that didn't have any hair gets kicked out by himself. So in this case, putting it into word or letters would be AC, whoops, try that, AB plus C gives CB plus A. So here I'm representing the boy as being the positive ion. So boys would be the positive, and I represent the girls here. Give it some hair up here on her, sort of crazy hair, as being the negative ion. So you can sort of see what's going on. Okay, so now we're going to talk about non-redox, and we'll get into the difference in the decomposition between redox and non-redox here in a little bit. Most often, decomposition that's non-redox doesn't go all the way to the elements. But we'll explain that a little bit more. Okay, because it's got to keep the charges. Now, double displacement or double replacement is like having two couples going to a dance, and they get in fights, and of course they don't want to go home with the person they got in a fight with, so they go home with the other person's partner. So you get them trading partners. So the redhead guy is going to go with the blonde, and the dark-haired guy is going to go with the dark-haired girl. Now in chemical lingo we would say A and B plus C and D yields A and D plus C and B. Notice I always kept the guys first, or the positive ones always go first, the negative last. Now they might not mix just exactly. We'll show you a whole bunch of different examples. Combustion is probably the favorite for most kids because of course it makes everything go boom, but it usually starts with a carbon compound with some amount of hydrogen and could have oxygen with it, but some kind of carbon compound plus oxygen, giving CO2 and water. Now, if I don't have enough oxygen, which firefighters worry about in the wintertime, then instead of, so I'm going to say not enough O, then what you get instead is CO, or carbon monoxide, and water, and that's where we get problems in our furnaces in the wintertime. So this is a combustion reaction. Most times if we end up with O2 and water or things like that, we'll talk about some other options that combustion could possibly do in a later video. But this is just the generals, okay? Okay, so let's talk about what redox is and what it's not. Non-redoxes, charges of all elements stay the same. And that's the important thing here. Non-redox, from side to side, an oxygen on one side is a -2 of the arrow, the oxygen on the other side is a -2. You're saying, well, how do they change? In a redox reaction, they do change. Remember that any element by itself has an oxidation charge of 0. So if I take something like the H2 that we did earlier plus O2 yields 2 waters, and we look at the charges of each of these. Any element by itself is 0, so we got a 0, a 0, but when they combine into water on the other side, I get a +1, and I get a -2. So the charges of hydrogen change from side to side, and the charge of oxygen change side to side. Now, hydrogen lost electrons and became more positive, and oxygen gained those electrons and became more negative. Now to remember what's going on here, because on redox what we have is we have oxidation that occurs and we have reduction that occurs. Well, how do I know which is which? And here's the key. Oxidation is LEO, or loss of electrons is oxidation. So that would be like hydrogen here. And GR, and that's an easy way to remember that I'm reduced, GR makes me mad, that is going to be oxygen. Oxygen is gained weight. So if I've gained weight, GR, this works really well for girls. If I gained weight, GR, I'm getting angry and I'm negative. I'm more negative. And oxidation, oh, it just sounds like OxyClean. I'm getting clean. I'm becoming more positive instead of being dirty. Then I am losing electrons or losing the dirt. Okay, so hopefully that will help. So redox is when I change charge side to side. I'm either oxidized or reduced. And non-redox is when I don't. Now, how did we get redox? Well, reduction and oxidation both have to happen at the same time. So if I'm losing electrons from one, I've got to be gaining electrons in another. Okay? And that's your intro to Chapter 5. We'll go into redox reactions more in the next video.